Good afternoon, everyone. Welcome back to room 305. I see we are full as normal. If you guys can try to get into the middle to find a seat, fire code and stuff like that, that would be very, very much appreciated. This is the last talk in our geophysics, geology and atmospheric sciences session, and it goes to Addison. And how do you pronounce your last name, Addison?
Banihirwe.
I'm going to leave that one with him and not even attempt it, who's going to talk about interactive supercomputing with Jupyter and Dask. Thank you very much, Anderson.
Thank you, Scott. Great. Thank you for having me here. This is my first SciPy, so I'm very excited to be here. So as Scott said, so my name is Anderson Banihirwe. I work as a software engineer at the National Center for Atmospheric Research. So for those who are interested, the slides are available at that address. So this is a talk about Python tools that enable interactive supercomputing, and we're going to see what we mean by supercomputing in a minute. Okay, so this is Alice, and Alice is a project scientist at NCAR. She studies the transfer of water and energy between the land surface and the lower atmosphere. And on the other side, we have a cool notebook of her work. There are three things that are really interesting about this notebook. So the first thing is that this notebook is not running on her computer. So this is running on a supercomputer. In this case, this is Cheyenne. And as you can see, there's an address to a Jupyter hub running on the Cheyenne supercomputer. The second thing is that she's using hundreds of processes and terabytes of memory. All this is distributed computing resources, thanks to dask-jobqueue. We're going to talk about that as well. And the third thing is she's actually doing science. So this is not a toy example, which is what she's good at. So now we're going to talk about how we at NCAR enable Alice and folks like her to do interactive supercomputing. So what do we mean by supercomputing? First, MPI, batch processing, lots of heavy machines that most of people don't have access to as admins, so you have to talk to people to be able to install some of the software. In the picture, so this is Cheyenne, which is a supercomputer operated by NCAR. If you're ever in Cheyenne, Wyoming, feel free to stop by. They give free tours of the facility if you want to. And what do we mean by interactive supercomputing? So with the current growth in data creation, both through new simulations and new observations, there's a growing need to have a more human-in-the-loop workflow, like where people can rapidly prototype and iterate through the data with tools like Jupyter notebooks. There's also a need to do things like in-situ data analytics. So instead of having to run the simulations and output the data, you could actually run the simulation and do the analysis at the same time. And the other thing is actually adaptive scaling of computing resources. So this combination would really be powerful, but it's really hard for different reasons. So some of these reasons are cultural and others are technical. So the first one is that HPC systems tends to be unique. So every HPC center has its own policies when it comes to things like security, what can you run on the supercomputer. And the second point is the tension between interactivity and machine utilization. So when it comes to HPC systems, HPC centers tends to be measured according to how often the machine is actually utilized. And when you're talking about things like interactivity, users want to have the resources on demand whenever they want them. But because HPC systems operate on batch queue systems, it's not that easy to actually get resources whenever you want to. So no user is going to wait for 5 hours to get into the queue to do interactive data analysis. And the third point is the lack of elastic scaling. And this is a huge, at least in my opinion, I think this is a huge disadvantage in that if someone, let's say, wants to do some analysis, they have to take time and actually think about how much resource they want before they even do the analysis. And what ends up happening is that you get into your work, maybe 5 minutes later, you probably take like 20 minutes thinking, what do I do next? And during that time, the resources are just idle. So it would be nice if you could actually scale down, let other people use those resources, and get them back whenever you actually need to. The good news is that despite all those challenges, there's a growing list of technologies or tools that try to help with interactive supercomputing. And I'm going to talk about some of these tools. The first one is Jupyter. So we all love and use Jupyter. And so I'm not really going to spend much time on it because now everybody is familiar with it. And some of you may be wondering, but isn't Jupyter already usable on HPC systems? And the answer is actually yes, but you have to go through all these steps. You have to SSH into the machine. You have to set up the SSH tunnels. And you have to do this every single time that you want to actually use the Jupyter notebook on the supercomputer. And this can actually be tedious, especially for new users. So what is missing? So one of the things that is actually missing is the multi-user support. So all those steps, everybody has to go through them individually. And it would be nice if there was one single place that everybody goes to and everything is done for them. Another thing is actually the lack of pure web access to HPC resources, because as you've seen, we're setting up SSH tunnel, which if you ever need to use another process that probably runs on a different port, so you also have to SSH to create a tunnel for that port as well. Well, then Jupyter Hub comes to the rescue. So one good thing about Jupyter Hub is that in a way, it provides a standard way of managing authentication. So one of the issues that is not really hard to convince sysadmins about is the security of web applications. But Jupyter Hub makes it easy in that it doesn't really force you to use any type of authentication. It's up to you to choose what you want to use for authentication. In this case, on the supercomputer, you have different types of authentications. And another thing is that Jupyter Hub will just take care of spawning the Jupyter Notebook single server and giving access to the user on demand. And so let's now switch gears and actually see how this works in practice. So I will skip these few slides and actually go to the live demo. So the first thing that you do as a user, so you just go to jupyterhub.ucar, .edu. And so this is what you're presented. And if you've used the Jupyter Hub before, this looks familiar. The only difference is that in this case, I have to use the same authentication that I use to SSH into the machine. So in my case, I just provide my username. And then for the password, it's a combination of a PIN number and a YubiKey token. So now I'm authenticated. So I then get this page, which basically asks me for the project account. So this is the allocation on the supercomputer so that they know who to charge for this usage. So in this case, I'm going to provide, I'm going to change the queue here and specify the project. And maybe just reduce the wall time. And then once this is done, I just click on spawn. And what this is doing in the background, it's basically submitting a job to the queuing system. And once the Jupyter Notebook server is ready, I will get redirected to this new page. And at this point, thank you, thank you. So at this point, you have the same interface as what you'd have on your laptop. So I can run notebooks, in this case, to show you that I'm not really lying. So this is, so you could just run this notebook, which is backed by bash kernel. And as you can see, I don't really have 200 terabytes of storage on this computer. So, okay. So yeah, so that's it about Jupyter Hubs. I'll come back to it later. So then the next tool is Dask. And is there anybody in this room who's not familiar with Dask at this point? Okay, a few people. So at this point, most of us are familiar with Dask. We've probably interacted with it in the cloud or even on our local machines. So I'm not really going to spend any more time talking about Dask. The one key point that I'm going to focus on is how to deploy Dask on HPC systems. And this is where dask-jobqueue comes in. So dask-jobqueue is a Python library that allows you to easily deploy Dask on job queuing systems such as PBS or Slurm, and so many other. It was created as a spin-off of the Banihirwe project. It provides a high-level Pythonic user interface to manage Dask clusters and Dask workers. So for instance, if you're like on a system that uses PBS as the queuing system, so this is what you have to do. So from dask-jobqueue, import the PBS cluster class, and then instantiate that class with things like the project account, the queue, and all other resources that you want. And I should be clear that I'm not really defining everything that I want in my cluster. At this point, I'm just telling Dask a configuration of what to ask to the queuing system every time that I want computing resources. So in this case, I'm saying every time just in this single job, ask for one process and one thread and 100 gigabytes of memory. And once that is done, you can manually scale it by basically saying just scale to 10 nodes. In this case, that corresponds to 10 Dask workers. Or you could actually tell it to scale adaptively by saying, okay, I want you to, at all time, to have a minimum of one Dask worker, and you can scale between 1 and 100 Dask workers. And Dask will basically monitor your usage of your CPU usage or your memory usage, and then it will know that it should get more resources. And at any point, if you're not using those resources, it will just tell the queuing system to kill those jobs. So if you're on a system that uses Slurm instead of PBS, it's the exact same thing with only one difference of just using the Slurm cluster instead. Okay, so now let's go back to Jupyter and actually see what Alice is actually doing in that notebook. Okay, so there's so much science going on in this notebook, so I won't really spend so much time going through the details about it. But if you're interested, there's a copy of this notebook that you can actually run in the cloud. It's actually exact same copy. So if you go to the Banihirwe data GitHub organization and just go to the Banihirwe tutorial, you should see one of these notebooks there. But I'm going to focus on a particular data set here, which is the gridded ensemble precipitation and temperature estimates over the contiguous United States. So this consists of 100 ensemble members for precipitation and temperature data. So the first thing that I do, I import some packages. Is this better? Okay, good. So the next thing that I do, I now create my cluster object by telling dask-jobqueue that I want 109 gigabytes of memory, 36 threads, and 36 processes, specify the queue and the wall time, and I tell Dask to scale between 360 Dask workers, and I don't know what that is, but you get gist. So, and when I click on this, as you can see, at this point, Dask is submitting a bunch of dask-jobqueue is submitting a bunch of jobs to the queuing system, and now I'm actually getting the workers. So, as you can see, I have 360 workers as I specified. Let me bring up the dashboard here. Okay. Okay. Let me one more thing. Okay. So now I can actually start doing the computation. So, but the first thing I'm going to do is actually connect my client to the remote workers. So I have a cluster with 1 terabyte of memory and 360 workers. So the dataset is saved in is stored as ZAR in ZAR format. So there was a talk 2 days ago about ZAR. If you've never heard about ZAR, recommend to go and check it out. So, and I use XArray to open this ZAR store. Again, just took 87 milliseconds. I didn't really do anything other than just looking at the metadata. So we can look at the size of the dataset. It's close to 1.7 terabyte. We can look at some metadata. So we have precipitation as one of our variable, the mean temperature and the temperature range. And these are all 4D variables. So 100 ensemble members for these many days, which corresponds to close to 40 years, I think, of data. And if you wanted to, you could actually look at the Dask array, if you actually wanted to look at the shape and things like that, if this is more useful to you. So the first thing I'm going to do is actually just do a quick plot for the elevation. This is basically a mask that tells me the elevation for each of the grid points. And as you can see, towards the west coast, you have points with higher elevation compared to the east coast of the country. So let's now try to quantify the ensemble uncertainty for a single day. So just select the data for 1 day and try to quantify the uncertainty for that 1 day. Again, this just goes very fast. Nothing really happened there other than just that Dask constructed the task graph. And when I do the plotting, that's when actually the computation gets triggered. Then I have my plot here. Again, I won't go into the details about the science. So the next task, let's try to compute the intra-ensemble range. Again, as you can see, this just returns quickly, but this is actually a delayed operation or a lazy operation. And now I can actually tell Dask to do the computation. So now you can actually start seeing some activity here. And it should be done anytime soon. Okay, so this is this has to do with Dask resiliency in that if, for instance, Dask tries to do a computation and it fails, it would start marking that computation. I think by default, if it tries 3 times and it hasn't actually been able to successfully complete that computation, Dask will just give up on that particular computation. So you could actually specify how many times you want Dask to try. Like, for instance, if a task was scheduled on a worker and the worker dies, what to do, or if you run out of memory or things like that. So this is basically a cool feature of Dask, the resiliency of Dask. So the computation finished. We can actually do some plotting here. Okay, again, not that many details about science. So the next task is, let's try to compute the average seasonal snowfall. In this case, we're actually just computing on only 4 ensemble members. So if you go through the distributed documentation, there's a really cool information about how to interpret the dashboard here, the information about the dashboard. So this is done. Now we can do the plotting. It's going to take a few seconds. And as you can see, so as the year progresses, so the amount of snowfall decreases. And I think this is in the summer, you don't even have any at all in most part of the country. And this is consistent across the 4 ensemble members that we're looking at. So let's now actually do something cool. Let's actually look at like a specific region. In this case, let's just look at all the grid points near Austin. So X-array is really cool in that you can just give it the coordinates of the points you're interested in. In this case, we provide a buffer so that we can actually get all the grid points in that range. And we're going to compute the maximum precipitation near Austin for the last 40 years. So it's going to take a few seconds. Okay. And then we can do the plotting once this is done. So yeah, so again, we can look at our cluster object. I still have 360 workers. I could have started with something really small, but it's just that I wanted this to go really fast. And you never know how busy the queuing system is going to be. So if you need the resources, you get them when you can. Okay, so this should be done. And basically, so this is the maximum precipitation near Austin, Texas, for the 100 ensemble members for the last 40 years. So you could basically look at what that looked like. So yeah, so at this point, if I basically don't do anything, because I told Dask that I want a minimum of 360 workers, it would just keep those resources. But instead, you could actually, now that I'm done with this, I can actually do let me just tell it to scale down to this. And basically what Dask is going to do is going to start monitoring the workers, and if I'm not using them, it will just take them away. So I will come back to this later to show you what I mean by that. Okay, so we've seen, or at least I tried to demonstrate the adaptive or the elastic scaling and the resiliency of Dask. And let's now talk about some of the challenges. So being able to know how much resources you need before actually doing the computation is really hard, and it actually requires quite a lot of experimentation. And even if you actually get to know how to do this for one particular workflow, it probably changes once you move to a different data set. So, and another thing is that the computational workloads, are not really constant. So you probably started with 1 terabyte of data. 5 minutes later, you probably only have 1 gig of data left. At that point, you don't really need all the resources that you started with when you're dealing with 1 terabyte of data. So the good thing is that Dask thinks about these things. So how to scale up and down, how to be resilient in case like a worker dies, and what if when you get new workers, what to do in terms of load balancing and things like that. So what is the solution? Basically just start a Jupyter notebook, instantiate your Dask cluster, and then just let Dask do the scaling up and down for you. And you just focus on the science. And what are the benefits to HPC systems for elastic scaling? One of them is that it actually improves the occupancy of the machine, in that if the resources are idle, then Dask knows how to release them so that other users can actually use them. And another thing is that with the resiliency, you can easily, for instance, if you started with 120 workers, for some reason, your worker dies, Dask will know how to get a new worker. And in a way, if you think about something like MPI, where you start, let's say you have like 120 workers. If one thing goes wrong in an MPI environment, the whole thing dies. So in a way, you kind of lose all the work that you had done, which is probably not that nice. So basically, another thing the same point, Dask thinks about these things, and I think you should also think about what you gain from this as well. Again, so not all jobs are interactive. So once you're done with your interactive workflows, there's this other package called dask-mpi, which actually now allows you to go on and actually launch batch jobs in case you don't need to do interactive data exploration. And looks like I'm running out of time, so that is pretty much it for today. Thank you. And like I said, now you can see that it took away those resources.
It ends at 3:05 the session, and the next one's at 3.
Okay, so yeah, we got.
Right here.
So do we have any more questions?
Hi, great talk.
Thank you.
How do you deal with large data sets? And if you need to import like large data sets, can you do it? Can you put them on the cluster, or you?
So in this case, the Jupyter Hub is actually running on the same file system, so which basically means that we don't need to move the data around. So in our case, it kind of works in that the data, basically we're moving the computation where the data is, so we don't need to move the data around. So I haven't run into cases where we need to move the data. If anybody has run into that, then they could probably provide a better answer.
Other questions? We have time. Oh.
Yeah, it's the Jupyter Hub instance taking a pre-allocated resources like 20 loads, and then you scale up and down inside Jupyter Hub.
No. So if you remember what I did when I logged in to the Jupyter Hub, I asked for, I think, just one process. Mm-hmm. So Jupyter Hub is actually running, the lab itself is running in its own job.
Okay.
So when I do the scaling up and down, I'm actually doing that as independent jobs.
Okay.
So that's why I'm able to do that.
But I mean, scaling down is easy. But when you're trying to scale up, in our cluster, you need to wait 30 minutes to have a new job created for you. So
yeah, that's what I say, that when it comes to queuing systems, I think that lack of elastic scaling kind of makes it hard to actually do interactive computing, in that you can't wait for 2 hours to get into the queue. In my case, I was able to get into the queue very easily because I had to ask a special reservation. So yeah.
All right, we're going to have a lot of people filing in and out here because we're changing topics. So can we please thank Anderson again and all the speakers for the Geophysics Symposium.